Welcome to this session of Materials Engineering. Myself, Anirban Sarkar, Assistant Professor, Department of Mechanical Engineering of JIS College of Engineering, Kolkata. Today's session, we will discuss about that crystal structure of material. Learning outcome. After completion of this session, we will understand the importance of crystal structure and its classifications. Now, what is crystal structure? First of all, we know that various properties of material are related to the structure. The structures are of many types, such as crystal structure, macrostructure, microstructure, etc. All these affects the properties of metal and alloys, and hence it is necessary to study these structures. So in this session, we will discuss about that crystal structure and related terms. The study of crystal structures is usually done by X-ray and electron microscope. The study of macrostructure is done by unaided eye or by using low magnification, using generally below 10 linear magnification. The study of microstructure is done by the optical or electron microscope using much higher magnification. Optical microscope provides magnification in the range of 60 into 62 2000x, whereas electron microscope provides magnification up to 5 lakhs. So, crystal structure deals with the atomic arrangement in the solids. They are three-dimensional pattern of atom in space. All metals, a major fraction of ceramics, and certain polymer acquires crystalline form when solidified. That is, in solid state, atom self-organize to form regular order of atomic arrangement through repeated periodicity at regular intervals in 3 dimensions of space. When the solid is not crystalline, it is called amorphous. Examples of crystalline solids are metals, diamond, and other precious stone, ice, graphites, etc. And examples of amorphous solids are glass, amorphous carbon, amorphous silicon, and most plastics. There is very large number of different crystal structure, all having long range atomic order. These vary from relatively simple structure of metal to exceedingly complex structure of ceramics and some polymers. To discuss crystalline structure, it is useful to consider atom as being hard sphere with well-defined radius. In this context, the shortest distance between two like atoms is one diameter. In this context, use of term lattice and unit cell will be handy. Lattice is used to represent a three-dimensional periodic array of points coinciding with atom position. Unit cell is smallest repeatable entity that can be used completely represents a crystal structure. Thus, it can be considered that a unit cell is the building block of crystal structure and defines the crystal structure by virtue of its geometry and the atom positions within. So while dealing with this crystal structure, the regularity of atomic arrangement in solids comes due to geometrical conditions which are imposed by directional bonding and or close packing of atoms. The most stable of atoms in a crystal will be that arranged which minimizes the energy per unit volume. That is, in other words, the one that number one may be defined, that is, preserves electrical neutrality. Number two, satisfy the directional and discreteness of all covalent bonds, minimizes strong ion-ion repulsion, packs the atom as closely as possible, constituents with electrical neutrality, satisfy the directional and discreteness of all covalent bond, and minimizes strong ion-ion repulsion. Now, the crystal structure observed in solid are described in terms of idealized geometric concept called space lattice. Space lattice is a three-dimensional pattern of points in space. This is also called as point lattice, which is shown in this figure. Now, every point in the space lattice has identical surroundings with that of every other point. These points in the space lattice with identical surroundings are called as lattice point. Identical surroundings means the appearance of a lattice point when viewed in a particular direction will be the same to the appearance of any other lattice point when viewed in the same direction. lattice point can be arranged in only 14 different arrangement or arrays. That is called Brevis lattice. The actual crystal structure will be similar to this 14 Brevis lattice and can be obtained by assuming atoms or group of atoms as a lattice point. There must be an identical atom or group of atom with the same orientation at every other lattice point. So in this figure, it is shown as an lattice unit cell with 3 dimension and unit cell of a particular with lattice point. Since the structure of the perfect crystal in a regular pattern of atom distributes on a space lattice, the atomic arrangement can be described completely by specifying atom position in some repeating unit of space lattice. Such a repeating unit of the space lattice is called unit cell. The size and shape of the unit cell can be described by the vector ABC. So if these vectors ABC, that means the arms are same, that will be the cubical one. These vectors defines the cell and are called crystallographic axis of cell. There may also be described in terms of their length and the angle between them. These length and angles are the lattice constants or lattice parameters of the unit cell. Thus, by giving special value to the axial length and angle, we get the unit cell of various shapes. If the vectors which defines the cell are chooses so that the lattice point are only one at corner of the cell, such a unit cell is called primitive cell and has only one lattice point per cell. The various crystal systems are the result of transitional repetition of these primitive unit cells in space, and all such crystals come to be 7. That means the 7 common crystal lattice are, that is, cubical cell, where 3 equal axes at right angle. So here in this figure, first of all, shows that system, lattice constant and angle, and unit cell geometry. So first of all, in a cubical cell, the 3 axes are equal and they are at right angles. So the lattice parameter, that is A. Next is diagonal. These lattice axes are three lattice axes at right angle. The two axes, that is A equal to B and the C is not equal to A and B. In orthorhombic structure, there are three unequal axes at right angle as shown in figure. That is the lattice parameter A not is equal to B, not equal to C, but the included angles, that is alpha, beta and gamma, are all at 90 degrees. Now next is rhombohedral structure. In rhombohedral structure, three equal axes equally inclined. That is, here the lattice axes, that is A equal to B equal to C, and they are equally inclined. That means that alpha, beta and gamma not equal to 90 degrees. Next is hexagonal structure. Two equal coplanar axes at 120 degree, third axis at right angles. That means the lattice axis A is equal to B but not equal to C, and alpha and beta, the included axis angle, are at 90 degree, but another angle gamma is at 120 degree. Next is monoclinic. In monoclinic structure, three unequal axes, one pair not at right angle. So it is denoted as A not equal to B not equal to C, and alpha equal to gamma equal to 90 degree not equal to B, beta. And last of all, triclinic. That is, in this case, three unequal axes unequally inclined and none at right angles. That is A equal to B not equal to B not equal to C, and alpha not equal to beta not equal to gamma, and even not equal to 90. However, there are other arrangement of lattice point which satisfy requirement of point lattice. That is the condition of identical surroundings. Brevis demonstrated that in all such lattice are 14, and these are called Brevis lattice. The 14 Brevis lattice are given by in this figure and table. The actual crystal structure can be obtained by placing atoms at Brevis lattice point or at some other points which have fixed relation to the Brevis lattice points. So in Brevis lattice cell, first of all, as we know, in a cubical structure, it may be P type, I type or F type. That means simple, I means that is centered, and F means that is face centered. So as we know, these axes are at right angle and all equal. That is the axis length, that is A equal to, all are equal, and they are at right angle. So what is the difference between these? That is, in a simple cubic, only the corner atoms are there. In a body-centered cubic, at cornered atoms are there. There are total 8 corners in a cubical cell. At center, 1 full atoms are there. And in a face-centered cubic, every face there are 1 atoms are present, which is shared by another adjacent unit cell. For example, copper, silver, sodium chloride, we can found this type of cubical structure. Then next is tetragonal. In tetragonal, we can found the simple tetragonal and body-centered type. So as we know, these axes are at right angles and 2 equals. That means the 2 axial lengths are same but not equal to the third one, and they are polar at 90 degrees. So for example, it is found in tin, titanium oxides, etc. For orthorhombic structure, we found that is 4 type of possible. One is P type, that is simple type, C type, that is centered, and I is body centered, and F is face centered. So in this, the axial and interaxial angles are, that is, these axes are at right angles, all unequal. The axial lengths, that is A not equal to B not equal to C, but their included angles are all 90 degrees. So in a orthorhombic simple type, the corner atoms are there. In a C type, the upper face and bottom face have shared by 1 atom, and in I type, that is 1 centered atoms are there along with corner atoms, and in F type, all the faces are shared by 1 atom. For example, gallium, we can found in this element, this type of orthorhombic structures is found. Next is monoclinic, that is P type and C types can be found, that is in gypsum. So here P type means that is only the simple monoclinic type, that is 8 corner atoms are there, and in C type, upper face and bottom face, 1 extra atoms are shared by adjacent planes. Here the characteristics is that 3 axes, 1 pair, not at right angles of other of any length. Another is, next is triclinic, which is found at simple type, that is P type. The characteristics is that these axes not at right angles of any length. And the example is, that is potassium chloride. Another is, that is trigonal, it is found only 1 type, that is rhombohedral. Trigonal, that is R, denoted as R. These axes equally inclined, not at right angles, and all equals. The axes are, that is same, that is A, B, C equal or are equal, and their adjacent angles 2 are equal and 1 angle is not at 90 degrees. That is calcium carbonate or calcitate, arsenic, and bismuth, we can found this type of structure. Another structure that is called hexagonal, it may be C or P type. In this case, these equal axis coplanar at 120 degree, fourth axis at right angles to this, that is given A1, A2 and A3, that not equal to C, and 2 mutually perpendicular angles, and the third angle gamma is at 120 degree. For example, zinc, cadmium and quartz, this type of structure is found. The simplest structure will be those obtained by placing of atom same kind at the point of the Bravais lattice. Metals may not exist with all of the above structure. The most common structure observed in the metals are body-centered cubic, face-centered cubic, and hexagonal closed packed. So, in this figure, the most common crystal structure and their properties are shown. So, in an unit cell of simple cubic, that is 8 corner atoms are there, and each atom is shared by 8 adjacent unit cell. So, in a unit cell, if we consider the total number of atom shared, that is 1 by 8 into 8, that is total 8 corner. So that is called average number of atom per unit cell, that is denoted as small n. In another case, that is the property which is very important, that is called coordination number. Coordination number is defined, that is the nearest equidistant neighboring atom, and in this simple cubic structure, that is 6. And the lattice parameter, that is axis E, and there are other parameter, the relations between that one, that is E and R, that is lattice axis, and the radius that is related by this, that is 4 by root over 4. And if we calculate APF, we can found, that is the atomic packing factor, that is 0.5. So these are all, this part will be broadly discussed into the next session. But in today's session, we need to know the most common type of structure, how they looks like, and what are the inside it. In a simple cubic structure, although this type of structure is not found generally in every metals, but to understand the other one, that is body-centered, face-centered, and hexagonal closed pack, first of all, this simple cubic structure we need to be understanding. So in a simple cubic structure, as described, there are total 8 atoms, corner atoms are there, and each corner atoms are shared by, that is in an unit cell, that is 1 by 8 of one atom. In a body-centered cubic, the total number of atom, that is 8 corner atoms are there as shown in this figure, and one complete atom at the center of the body, that is the body-centered cubic. And in body-centered cubic structure, the average number of atoms, that is 2, coordination number is 8, and the relation between lattice parameter and radius, that is 4 by root 3, and the APF, that is atomic packing factor, that is 0.68. In a face-centered cubic, the total 8 corner atoms are there, and each and every face there are 1 atom shared by 2 adjacent units. So accordingly, the average number of atom, that is 4, coordination number is 12, and the relation between A and R, that is 4 by root 2, and FEF is calculated, that is 0.7. Next is hexagonal close pack structure. So as this is a particular in hexagonal type, so there are one upper face and bottom face contains 6 corner atoms of an hexagon, and one face atom at lower and upper hand, as shown in this figure, and there are 3 interior atoms solely in this hexagonal close pack structure. So average number of atoms, if we calculate, that will be given 6, coordination number is 12, and the APF will be, in this case, that will be as usual as 7.74. So the important properties of the unit cells are, that is the type of atom and their radius R, cell dimension, that is the lattice spacing or the lattice parameter, that is ABC, and in terms of R, that is very important, and angle between these axes, that is alpha, beta, and gamma. And N, that is number of atom per unit cell, we need to be calculated. Cn, that is the coordination number, and APF, the atomic packing factor, which is the fractional volume of cell actually occupied by the hard sphere. As we have described earlier, that while calculating these things identically, we consider that each and every atom is an hard sphere. So although we know that atoms, the subatomic particles are there, that is proton, neutron, and electron, and there is a large vacant space, as if we analyze that is microscopically. But to analyze, simplify in this materials engineering, the simplifications are there. We need to be considered the atoms as an hard sphere. So with this, we are likely to conclude this session. These are the recommended books and notes are available. Thank you for joining this session.